Hello, calculus people. I owe you a couple of examples today. We're going to take a quick peek at integrating across vertical asymptotes. So we have a couple of those examples for the improper integration section as well. So let's just jump right into the examples. The first one I want to look at is the integral. Let's look at the integral from 0 to 3 of the following. So dx over x minus 1, or this is 1 over x minus 1 with that differential dx attached. And the first thing I want you to notice here is if you didn't know that there was a vertical asymptote here, so in green, we're going to do the wrong thing. And the wrong thing would be to kind of ignore the fact that there's a vertical asymptote at 1 and just pretend that we're going to integrate this normally. Now, we've seen that these kinds of things become the natural logarithm of the denominator. So in our case, this is going to become the natural logarithm of x minus 1. And if we're doing this the wrong way without considering the vertical asymptote, we might be tempted just to put x equals 3 and x equals 0 into this. So let's go ahead, let's substitute x is equal to 3. That's going to give us ln of 2. And then we're going to get a subtraction of a ln of the absolute value of minus 1. So if we kind of do this the wrong way, we would get a final answer of the logarithm of 2, and that's unfortunate because we're going to actually show that this is a divergent kind of integral around its asymptote. So yeah, you have to be very careful, I think. I think most of the time on the final exam, we'll be very explicit as instructors, and we're going to tell you that, like, hey, this thing has an asymptote. Please use improper integration. I think that's a very common thing that I've noticed on the final exams. But if you are doing practice questions, especially at the end of the section or the end of the chapter, just be mindful that the textbook may not necessarily tell you that there's a vertical asymptote that you're integrating around. So just be mindful of that. So look at your denominators, right? Look at your factored form of your denominators and just double check that you're not integrating around an asymptote if you have numerical bounds. So the right way to do this is to basically say there's a vertical asymptote at 1. And so that's going to be a problem when we go to integrate here. So what we're going to do is we're going to chop up this integral into 2 separate pieces. So we're going to go from 0 to 1. And then we're going to go from 1 to 3. And then what we're going to do is we're going to tackle each one of these separately. And we're going to essentially do what we did with infinity. And that is we're going to set up maybe a variable up top or at the bottom here. So we're essentially going to be taking this number 1, which is the problem. And we're going to be inputting some kind of constant number, and we're going to allow the limit of that constant number to tend towards the number 1. So let's take a look at this first integral first, and let's kind of see what happens with this one. So let's sub, I don't know, k in for 1, just for now, for that upper bound. And we already know how to find the antiderivative of this. Oops, this should be an x, not a k. My apologies. We already know that the antiderivative of this is the logarithm of x minus 1. And we're going to evaluate that in between x is equal to k and x is equal to 0. So what we have here is we are going to get the logarithm of k minus 1 minus the logarithm of absolute value negative 1. So that's going to disappear. So we're going to get the logarithm of k minus 1 as our final antiderivative here. And then what we want to do is we want to consider what happens as k gets closer to 1. So let's consider the limit as k gets closer to 1. And we're going to let k, we just have to be kind of careful because this is going to be technically a one-sided limit. So if I look at, my lower bound is 0, my upper bound is 3 in the original one, and we're kind of slicing it here at the number 1. So this first integral is trying to calculate the area in here. So we're going to be approaching the number 1 from the left-hand side. So I am going to use that little minus notation here. I'm going to say that I really want to approach the number 1 just from the left-hand side. So we're going to be considering decimal numbers that are slightly smaller than the number 1, okay? Just kind of when we want to go think about some of these substitutions. Okay, if we consider values of k that are slightly less than the number 1, we are going to get a negative number here, right? When we do our subtraction. But the inside part here, this is going to be getting closer and closer to 0. Right, so it doesn't really matter if I have a positive or negative inside part of the logarithm. I have the absolute values. So the absolute values are going to make that into a positive number, and then I'm going to be getting something that's tending towards the logarithm of 0. So this limit is actually tending towards negative infinity. Okay, so this just comes from our understanding of what the natural logarithm looks like. It's a function that looks something like this. Okay, so as that inside portion gets closer and closer to 0, from the right-hand side, we have that vertical asymptote for this logarithm. So this very first integral that we've done, the integral from 0 to k of 1 over x minus 1, we already know that it's not possible to find an area for this particular integral. That means if I go back to where we started up here in the consider statement, since we can't find an area for the first integral, it doesn't really matter what I add to it. This whole original integral is going to be divergent. So I don't really have to worry about this second integral. It's probably also going to be divergent. But yeah, as soon as one of the two integrals that we're looking at is divergent, then we know the entire thing is going to be divergent. So therefore, we don't really have to consider the second one. So we don't really care about this second integral. And that's because we know the integral from 0 to 1 is already going to be divergent. So as soon as 1 is divergent, then we know that overall starting integral is going to be divergent as well. So therefore, our integral from 0 to 3 of 1 over x minus 1 is divergent. In other words, it doesn't really make sense to define an area for this because essentially what's happening is the function's not approaching that asymptote fast enough. So because it's not approaching its asymptote fast enough, we can't really talk about the area. It's actually technically an infinitely sized or an infinitely big area. So there you go. That's kind of working with an asymptote is very similar. You just have to be a little bit mindful, I would say, of which side you're approaching the asymptote from. That's going to affect how we write down the limit a little bit. But yeah, other than that, a very similar approach, I would say, to what we were doing with those infinite limits. And it's garbage day this morning, so I apologize if you hear lots of loud banging in the background. it will soon be over. In the meantime, let's write down our next integral that involves a vertical asymptote. Let's see if it's possible to calculate the region from 0 to 1. So we just talked about the logarithm function up here, right? And we said the logarithm function actually has a vertical asymptote at x is equal to 0. So is it possible to integrate around or very close to that asymptote? Can we actually find a region from 0 to 1? 1 being where it crosses the x-axis. So in red, is it possible to kind of find this? Is it possible to find that shaded in region? Is that a thing that we can define an area for? I don't know. Let's find out. Okay, so what we want to do first is we would like to note where that asymptote is. So ln of x has a VA at x is equal to 0. So what we're going to do is, instead of evaluating this integral straight up, we are just going to sub in some kind of parameter at the bottom bound here. Okay, so we're going to evaluate this integral instead. And if you need to, go back to your formula sheet. We have done the integral of the natural logarithmic function, and the antiderivative of this function is x ln x minus x. So you should be able to go straight to your formula sheet and grab that antiderivative. This is a special case scenario. If you don't remember that or don't have that on your formula sheet, it's possible to use integration by parts to evaluate this integral. Okay, and we would like to evaluate this in between 1 and k. All right, so since the upper bound is 1, let's start putting that in. So we're going to get 1 logarithm of 1 minus 1. So there's the x equals 1 bound. And then let's subtract the x equals k bound. I'm going to get k. Actually, these can be circle brackets. K ln k minus k. All right, we know the logarithm of 1 is 0, so this first bracket becomes -1. And then we're going to get a subtraction of k ln k and an addition of k. So this is what our number is going to look like. And then what we need to do is we need to let the parameter k start tending towards 0. Okay, so we want to consider k tending towards 0. And if we kind of look at our bounds here of 0 and 1 for the logarithm, we're going to be tending towards 0 from the right-hand side. So we're only really going to be considering small positive values of k. All right, so if you need to, draw yourself just that little diagram just to kind of help you figure out what that limit is going to look like. So we would like to consider the limit as k gets closer to 0, but from the positive side, right, from the right-hand side, so a little plus sign here, of this expression. All right, I'm going to break this up into 3 limits across the subtraction and addition sign here. So we're going to have the limit as k tends towards 0 from the right of -1. And then we're going to subtract the limit as k tends towards 0 from the right of this expression, k ln k. That's going to be the hard one, I think, to do. Then we're going to have the limit as k approaches 0 from the right of k. That's the easy one to do. So, of course, this first expression here that I'm going to underline in red doesn't have any k's in it whatsoever, so this limit's just going to be a -1. This last one does have a k in it, and we know that k is tending towards 0, so this limit tends towards 0. It's going to be this middle limit that is going to be a little bit potentially tricky for us to figure out. Since it's online, what we could do here is we could bounce over into Desmos and take a look at what this function looks like. So we could look at the function x ln x to get a sense of where that function is going. So I'm just going to pop open Desmos. And hopefully that'll give us a good idea of what that limit looks like. Of course, since this is a limit, what you could also do is set up and execute L'Hopital's rule if that's something that you wanted to do as well. Which I will show us how. I might as well show you how to do that algebraically here, just to refresh your memory too. But let's take a look at x ln x. Okay, so this is interesting. So we have a function, and we're tending towards 0 from the right. So we're going to be zooming in, and it looks like we're going to be getting closer to 0. So it does look like this limit should end up being 0 based on what Desmos says. Let's see if we can come back and actually show that in an algebraic kind of way using L'Hopital's rule. So I'm just going to write down in red, so Desmos. So it appears to be equal to 0. This would be enough. Like if you're doing a WebAssign or something like this, or doing one of the weekly quizzes, you can just use Desmos because there's no need to show me any of this algebraic procedure. If this was something like the final exam and we wanted to see that work, you probably would have to set up and execute L'Hopital's rule. So I will show you how to do that here. And it's really just a matter of trying to arrange this expression in a way so that you have a numerator and a denominator that are tending towards the same thing. So let's keep the logarithm of k in the numerator, and let's move this k down into the denominator by making it a fraction. Okay, so k times ln k is equivalent to ln k divided by the fraction 1 over k, because you could just flip and multiply that fraction. So now we're in good shape. As k tends towards 0, both of these things are tending towards some kind of infinity. So I have an infinity over infinity kind of form. I can apply L'Hopital's rule to this expression. So this tends towards infinity over infinity form. So let's go ahead and apply L'Hopital's rule. And applying L'Hopital's rule it tells us we should take the derivative of the numerator, which is 1 over k, and we should take the derivative of the denominator. When you take that derivative, you should end up simplifying it to something that looks like this. So it should look like k to the minus 1. And then when we apply the power law, we get -1 times k to the -2. And then I'm just simplifying it to look like -1 over k squared. So there's a little bit of algebra here to get that denominator to look like a form that's helpful for us. And we're just going to keep the same limit. So remember that L'Hopital's rule does not change where this limit goes. It just says consider this new limit by taking some derivatives. Now, I don't need to bring down the +0. That's just going to disappear on us. But now I have the capacity to simplify this fraction a little bit. So we're going to get 1 over k times k squared over -1. So I'm going to flip and multiply. That's going to land us with, I believe, a -k in the numerator. And so we can see that that's going to tend towards 0. Okay, so L'Hopital's rule does tell us that that will now tend towards 0, and then we get a final answer here of -1. So that's interesting. That means that, this logarithm function, we could technically define the area around its vertical asymptote. So, a way to think about this is that the logarithm approaches that vertical asymptote quick enough that eventually the areas that we're adding on as we kind of go downwards are getting very, very close to 0. All right, so this is a convergent kind of integral. So therefore, 0 to 1 of the natural logarithm is convergent. And if we needed to, we could actually define this area to be 1. So there you go. There's a couple examples of utilizing the same kind of procedure, this improper integration procedure, to find areas or not find areas. So the key takeaway here for the improper integration section is if you have a bound of infinity, or if you know you're approaching or trying to integrate over a vertical asymptote, then what we really do is we try to use the fundamental theorem of calculus to get to an answer. The answer just involves some kind of parameter. We've chosen k to be that parameter in class. And then you have to evaluate a limit. And if that limit tends towards something that's a number, you're good. If that limit doesn't tend towards something that's a number, so it explodes off to infinity or minus infinity, then you have divergence. So if it simplifies to a number, you have a convergent kind of area. It makes sense to talk about that area as a number. Otherwise, we say that that integral is divergent, and we can't really talk about that area. So I think that's good enough for improper integration. Hopefully that gives you a couple examples there to kind of bounce off of with regards to maybe a future assignment. And then what we're going to be doing next week is we're going to be taking a look, introductory look at series. So series is kind of the next big step. So instead of looking at a sequence of numbers, which is just a number after a number after a number, we're actually going to start adding those numbers together. And we're going to start to see if the sum of those numbers tends towards some kind of y value as well. And this will essentially be the last big chunk of the course. We're going to be utilizing series to give the preliminary definition of what an integral actually is, so actually defining it in a bit more of a rigorous way. And then we're going to see how some functions can actually be better represented by series instead of something else. So that's kind of coming down the pipe works over the next couple weeks. Hopefully you guys have a great weekend, and I will catch you guys in class, hopefully, on Monday.